Please note that you're being recorded from now on. Hi, Hannah. Hi, Elena. Okay, everybody's coming on now, slowly. So, we are, for today, we're back to a remote session. We will be back in class on Monday next week, time as ever. So I have here the attendance records from who you joined, so we don't have to do formal attendance. I can do this afterwards. Okay. So hope everything is well and you're feeling all right. Hope this is not too much of an adverse situation. Hi, Amira. Hi, Jocelyn. And so for today, we're online and we will be back in class on Monday. So I'm just quickly pulling up the syllabus so we can quickly chat about the syllabus. I hope you all see my shared screen at this point. So we are today at module 8. We will be talking about chapter 6. Chapter 6 is the normal curve, which is, as you can imagine, for parametric testing, which we will basically spend our time for most of this class. Really the most important kind of basic concept which we have to discuss. So I hope that the homework was fine. So the homework is due tomorrow. In case there are any questions about the homework, we can talk about this afterwards, after lecture. And I think practice lab 1, I hope this was all fine. I yet have to grade it and I will be working on that this weekend. I have a lot of catching up to do after my travels, so I apologize that I'm lagging behind a bit. So, but today's module 8, we'll talk about the normal curve, standardization, and the STAT scores. So, what does this all mean? So, we are basically looking at chapter 7 in Norton and Heinzen. I hope it's gonna do what it's meant to do. Yes, okay, good. Okay, normal curve, standardization, and STAT scores. So what does that mean? We have talked about the normal curve. The normal curve is a bell-shaped curve, unimodal in nature, meaning it has one peak. It is symmetric, and it is defined mathematically. What does that mean? It's defined mathematically. For this very reason, I have prepared a little Excel spreadsheet. And you have this all on your module. And this is something I specifically wanted to do and show you because it took me quite a while to actually understand all of this in detail. And I was not sure I understood that before, that you actually can mathematically define the normal curve. And this is the arithmetic equation to define the normal curve. So this y here on the y-axis is defined by the x, defined here by the mu and the sigma, and pi as 3.145678. So essentially we have here with the STAT scores, the mean to easily define and to depict the normal curve using this formula. And the spreadsheet I have posted in the lab on the module will essentially allow for you to play around with this curve. So you can change the means, which here is the mean of 7. You can change the standard deviation, so you can see different shapes and forms. It's just, it's a funny kind of exercise, and it's also, it helps the understanding because a lot of these exercises that we're doing essentially underlies under the assumption that we understand this function. So this is what is meant here with it is defined mathematically. So it is a function of mean of individual points on the x-axis. It is defined by the mean and the standard deviation. So this will define the normal curve, as we know, and this is the basis for why we are actually able to do what we're doing, because knowing this function allows us to use this function to characterize the so-called area under the curve, and this will come later on. So this definition of mathematics is important. And the normal curve essentially is, just like I mentioned, it is the foundation of all inferential statistics. And again, inferential statistic means that we're quantifying probabilities and we're drawing inferences based on these probabilities to one individual or to a sample within the population. So the sample size is important in relation to the normal curve. So, and this is a little harder to see, but it will get obvious with the visual examples that Nolan and Heinzen have provided. So the sample size will essentially, when it's increasing, make the distribution more and more resembling the normal curve. So this normal curve, this classically beautiful normal curve that you see, data does not necessarily look like that, obviously, because it's you have some outliers and you have some more there, but essentially it will resemble the shape of a normal curve, but it will not strictly follow this normal curve. And this is important to keep in mind, because the greater the number of observations are in your normal curve and the higher the size of your sample is, the closer it gets to the size of a population, the shape of the distribution tends to be more normally distributed, or seem to be more normally distributed. Well, normally distributed is not a quantitative term, but essentially it will more and more resemble the shape of this normal curve. So this is important to keep in mind. And Nolan and Heinzen have actually done a pretty good job to show this by showing here data. And this data is, so we will see now 3 graphs with an increasing sample size. So what we're seeing here is the so-called happiness score. So the happiness score, and you may remember that we have seen a bubble graph in one of the earlier sessions, and I think it was session 3 when we talked, oh no, session 2 when we talked about visual displays. The bubble graph actually showed socioeconomic impact within the country and the happiness score as a function of GDP, I believe. And so this data from this happiness score is again here shown by Nolan and Heinzen. So we're seeing here a sample of, this is a histogram, right? So we have 1, 2, 3, 4, 5. So we have 5 countries. It's a sample of 5. It doesn't really look like a normal distribution. They have basically shown here like the perfect example of a normal distribution on top. Also, they're overlaying the bins. They're doing the same here with a sample of 30. So here we have 30 individuals, 30 individual countries. It kind of moves in that direction, but it's still not a normal distribution. However, when we really start improving the number now and we're going up to 157, well, you could make the argument that this more and more starts to look like a normal distribution. It's still not a beautiful normal distribution, but it kind of goes in the direction. So this is the point that I really want to make. And so it's quite obvious when you look. So now we're looking now at this increasing sample size that essentially makes the shape of the distribution look more like the normal curve. So now the question is, can you think of other variables that might be normally distributed? So I don't know. Somebody has a suggestion. Anybody has an idea what could be a variable that is normally distributed? Any thoughts, any ideas, any suggestions? Well, to make it easier for you, it's essentially everything that kind of follows where you need the set value that something functions. When you, for example, when you think of something that pretty much most of the physiological markers, demographic markers, age, all these things do essentially follow normal distributions. So, and that has a simple reason, right? So when you take 100,000 people in the age of 20 to 30, and they are obviously, and most of you will know. So I think if somebody asks you for an example along these lines, just think of it that way. There's a reason an individual has a blood pressure of 120/80. So there's a reason for that, right? Because the body needs it. So everything that has a set value will to some extent always tend to gravitate towards this set value. So if you have 100,000 men between 20 and 30, and you measure all their blood pressures, they will want to have a blood pressure that is quote unquote normal. And the outliers will be, I don't know, these will be the athletes that essentially have like really strong hearts that essentially may have a little bit of a lower blood pressure when they're not exercising. Then you have those that essentially have some comorbid condition and they may have higher blood pressures. But essentially all of them will gravitate towards the center, which is kind of the quote unquote normal value, given that all other factors are the same. So that means like same age group has an impact on blood pressure, gender has an impact on blood pressure. So women tend to have lower blood pressures than men because women do have hormonal protective factors, prevents them from cardiovascular disease and high blood pressures for a certain period of time, which disappears then with menopause. But essentially you will gravitate towards the center. That means it's more likely to have a normal distribution. So physiological parameter, many are basically normally distributed. So keep that in mind when you think of examples for normal distributions. Other examples, and this is what is shown here. So continuous variables are more likely to be normally distributed. Some are not, obviously. So for example, when you have variables, such as those of you that go into the realm of psychology, you will have survey data. Survey data may be continuous data, but not necessarily unnecessarily normally distributed, depending on the survey, depending on the question. But this is an example where basically you would not necessarily see a normal distribution. It's not a physiological parameter, right? It's different than having a physiological parameter versus a survey question. So now the question, can a nominal or a categorical variable ever be normally distributed? Is that actually possible? Any guesses? It can't be. Think of the definition of a histogram. How do we depict histograms? What do histograms depict? Histograms depict a frequency or a count as a function of a continuous variable, continuously, right? So it's the depiction of a frequency as a function of continuously depicted continuous variables. So when we have a categorical variable and we have here, I don't know, we have, for example, survey responses, how's your general health on the scale from 1 to 5? And you have 100 individuals check 5, and you have 100 check 3, another 101. Essentially, this is not a normal distribution, right? It's not a continuous variable. It's basically, it's defined, but it's integer response categories that are essentially ordinal in nature. So there's no room for normal distribution. So as per definition, there can be no normal distribution with categorical variables. Even when you have like, well, it is true in this format. It is not true when you think of a frequency distribution, when you think of a probability distribution. But that's a different conversation, please. We will talk about this later on. So when we talk about binomial distribution, it's going to become a different conversation. But in principle, categorical variables are not normally distributed. So, and now we're coming to, are there any questions so far? So normal distribution, I think it's rather intuitive. It's not that complicated. Increase in sample size will more likely show a normal distribution. And everything which we will be doing now for the rest of the semester is basically basing on the fact that we understand the normal distribution. So what is key to understand the normal distribution and to characterize the normal distribution is the so-called standardization. Standardization is a way to convert an individual score. And again, we're looking at a histogram that has frequency on the y-axis and a continuously depicted continuous variable on the x-axis. So if we are looking now at an individual score, that individual score, which is being referred to here, is essentially one score on the x-axis. And standardization is a way to convert an individual score on the x-axis with a known mean and a known standard deviation to a so-called set score. And the set score is in essence depicting the distance of the individual score from the mean in standard deviation as a difference metric. What does that mean? If I have a blood pressure of 120 in my population as a mean, this is my mean. This is what set equals 0. If I have a standard deviation of 15, this is going to be 153. And this is going to be 105. So a set score uses the standard deviation to characterize every point here on this entire x-axis. Independent of whether it becomes a decimal or not, you're doing nothing else but using this formula. You are subtracting from your individual point x the population mean, and you divide it by the standard deviation. The resulting set will be the distance of the point from the mean expressed as number of standard deviations. Does that make sense? Is everybody with me?
Yeah.
Thank you.
Yes.
Okay, is somebody not with me? Okay, good. I like the thumbs up. Okay, great. Okay, thumbs up.
I have a question.
Yes, please. Absolutely.
What do you mean by converting it to a set score? Like, are you changing the, like, what are you doing to it? Like, are you changing the values themselves, or are you just doing it? I don't get that part.
Okay, thank you. Thank you. So, because I was already anxiously waiting for somebody asking the question, what is this about? And so now I want to practice this in an example. So we have now, again, we have this equation. So I have digitalized the data from the happiness score. So this is the data that Noah and Hans are working with. And they have somewhere stated the reference, and I put it out of the original data file. Okay, so this is the equation. This is the set, right? This is 157. Let's copy this too. This is our histogram. Okay. So where's the mean? if it were a normal distribution, which let's assume it is, because that assumption is super important. The mean will be exactly where the highest spot is. It's where the mode is. In a normal distribution, the mean, the mode, and the median are on the very same spot at the highest peak of the normal distribution. In a perfect world, we don't live in a perfect world, but we're ignoring that for now. It's at the highest peak. Good, we have this high peak. This is our mu. We know the standard deviation. This is our sigma. And now we want to have the x. Good. What x are we interested in? Okay, so let's calculate first the mean. How do we calculate the mean? We know that. This is the sum of B2 to B. No, that is too much. It's far too much. It's 157 and 158. So it's B2 to B158 divided by count B2 to B158, right? That's what I mean. That's 5.382. Now we want to have the standard deviation. The standard deviation is now in essence, okay, let's quickly do this. We're doing now doing the deviations. This is the x minus x bar. Now we do x minus x bar square. This guy. That's our square deviations. And now we do this x minus this. Lock this in. And now we do this squared. Now we're just pulling this down. Come on. Okay, that's 158. Okay, now we do sum of squares. This is equal sum of D2 to D158 divided by count D2 to D158. Right? So that's our standard deviation. So now we have.
Wait, can you, is it possible for you to zoom in? I can't see what it says.
Sure.
What was the formula for the standard deviation again?
Well, it's the sum of squares, right? So we have the deviation, we have the score, we have the mean. We're subtracting the score from the mean. We're squaring the difference. That's the squared deviation. Then we sum these squared deviations and divide them by the count of all entries. So that gets us to the variance. And thank you for actually reminding me, because we actually need to do an SQRT. Okay, so we have now the standard deviation of 1.14. So it's the square root of the sum of squares divided, and so we get with the sum of squares divided by the count. We're getting to the variance, and taking the square root on the variance gets us to the standard deviation, right? So now, let's say we want to have the set score for a happiness score of 7. How would you calculate that based on that formula? because you know your mu, that is sigma. So you know the mu, you know the sigma. And if you have an x equals 7, you calculate now 7 minus mu, which is G7, G6, divided by G7. So you know now that your x equals 7 is a set of 1.42. And that's powerful knowledge, because essentially you know now that you can characterize every single point with your mean and your standard deviation, and you are transforming your individual score, and you're reducing the dimensions that you actually need to only needing to know the mean, the sigma, and the set. Because each individual point on here, each individual happiness score here will have a certain set. So there will be a corresponding set. So if you want to know and understand your sets for your individual entry, this is essentially nothing else but your individual score minus $G, $6 for your mean divided by $G, $7. Does that make sense?
Could you repeat the process again? Like, what is the $ means?
So it is X, that's your individual entry. It's either an arbitrary happiness score that you're interested in, or it's a happiness score of a country you're interested in. Let's say you want to have the happiness score of Canada. Beautiful Canada is 1.7766 set score. So you can characterize with just knowing the mean and the standard deviation all your individual entries. So by that, you are basically achieving something that is very, very powerful and very, very useful. So you can do this for your entire population, quote unquote population. Yeah, subset of countries. Excuse me?
What do you mean to characterize it?
So you're characterizing it based on your entire population. You have a world population, including all the countries of the world, with all of these countries providing you a happiness score. So you're characterizing a population of countries, of all the 158 countries that you're interested in or you have data from. And you're characterizing them, meaning you show this normal distribution, because this normal distribution will be the same for your actual happiness score, but it will also be the same for your set scores. So the shape of the distribution doesn't change because you're dividing them. So you're subtracting them and you're dividing them by a constant, which essentially you have characterized, you have basically found or calculated from your own population. So going back to this example, this normal distribution is actually calculated based on the set scores. The same story. You can do this for each variable and each continuous variable that you're interested in. And this for one very, very important purpose. Because you want to understand things independent of their nature. Because the central tendency and the variability are two useful markers to essentially give you an insight of how each individual score looks like. And it gives you the possibility to compare apples with oranges. And I actually like this depiction because that's actually quite exactly what we're doing, right? If you want to compare, let's put it that way, you assume that the change in a laboratory parameter associates with a change in blood pressure. You cannot directly relate these two. You need to find some way to bring them to the same denominator. You need to bring them on the same level, on the same dimension, to understand what is going on here and to find this relationship. And this is what we will be doing with correlation and regression. It's the basic principle of that. You're trying to reduce the dimensions of your parameters and to try to get them on the same kind of dimension. This is what you're doing with standardization. So you standardize every individual entry using the mean, the mu, and the standard deviation. Yes. Yes, Eden, you had a question?
Yes. So all like every set of data that is a, how did you call it? The standard, not standard. This normal
That is
curve.
normally distributed. Yes.
A normal distribution, so it should have the same standard deviation, right?
No, it does not have the same standard deviation, but the standard deviation will characterize, will allow for you to understand how does it shape. You know, when you assume this to be a bell-shaped curve, right? It looks like a bell. Well, not really strictly, but it's like somewhat looks like a bell, right? Yeah. And if you assume a standard deviation that is, so the mean will just shift the entire bell to the right if it's larger mean, or to the left if it's smaller mean. The shape of the bell, so whether it's more a Rubenesque bell or more a skinny Gothic bell, this will basically be determined by the standard deviation that is either smaller or it's large, smaller or large. So essentially, yes.
No, so a normal distribution is anything that is just symmetric, and the mean is the, like, it could have a lot of shapes. It could be very narrow and it could be very,
yes,
like, as long as
yes.
it's, oh, I thought it's just a specific curve.
Correct. It will always take the shape that looks somewhat bell-like.
Okay.
Don't nail me down on the bell here, but essentially it's the definition, right? It's a symmetric, unimodal, bell-shaped curve. That's what we're seeing here. It has two quote-unquote tails on the side. These are labeled tails. It has one mode, and since it's symmetric, it's supposed to have as many outliers on the left side and on the right side. And we're looking at a symmetric distribution, and the mean, the mode, and the median is going to be the same, and it's exactly there where the mode is, where the highest occurrence of the most frequent point is found. Okay, that's the normal distribution, and this is the basis of everything. And whenever you have a negative score, a negative set score, you're going to have a smaller dog. If you're to the right and you have a positive set score, you have a larger dog. So essentially, the sign gives you an idea, where does my individual point now stand in reference to the population? So if we're looking now at our happiness scores, so the average happiness of the world is 5.4. I take it, right? And now we're going down, and we're looking here at the less happy countries. And well, so where is now our junction point? So essentially, Turkey is average happy. So they're like 0.06 SAT score. So now Montenegro is a little unhappier than the average. Lebanon, Tunisia, Greece. Greece is unhappy. Well, they get all this money from the European Union. They should actually be happier than that. But it's so if we're going a little bit more to the happier side of things, Spain is super happy. Well, who has been in Spain knows why they're happy, right? So it's this basically, it gives you an idea in reference to the average in the world, right? To that average that you have found for all the countries. Well, that Spain is as happy, Algeria, Qatar, and Guatemala, that is actually very interesting. Argentina, Mexico. Okay, I've never looked at this data really. Well, here's Austria. We're pretty happy too. Good. Okay, so this is essentially what the SAT score is doing. Are there any additional questions to that? Or is kind of the concept clear? We are characterizing each individual point on the x-axis in reference to the mean, and we're using one population-specific marker, which is our standard deviation, the population standard deviation, not the sample standard deviation. Clear, right? If any questions, please speak now or read it up below on the top. Okay, good. Let's carry on. So now, obviously, when you have a SAT score, you can do just the opposite. And when you, so let's say, so you want to calculate a SAT score, this is easily done by subtracting your individual x. You subtract the mean from your individual x. You are dividing this difference then by the sigma. If you want to do the opposite, you're doing the same thing. Just you rearrange the equation. So you will first multiply the left-hand term with the sigma. By that, you get rid of this sigma. And then you just need to add the mu to your set multiplied by sigma, and you're basically calculating your x. So if I want to have, I want to know what score is a set of 1.235 or 4 multiplied by sigma plus mu, that would be a happiness score of 6.7865. 6.7865, that's approximately where Mexico is. Okay, so each individual entry gets a SAT score. You get a SAT score, somebody throws a SAT score, you can calculate where the positions in the rows go. And you will need that for the practice quizzes. So please make sure to review what we're doing here. I will post the actual in-class calculations later on. But make sure this is really, this would be such a pity to miss any points on that on the midterms. Please really make sure you know that. Okay, key terms. A set distribution is a normal distribution of standardized scores. This is what I meant. If you have raw scores that form a normal distribution, you transform the whole thing in SAT scores, still a normal distribution. So that's kind of the no-brainer of the whole operation, right? You do that to essentially compare apples with oranges, because regardless of the nature of your scores or your data or your variables, if you standardize it based on your mean and your standard deviation, the resulting SAT score, you can compare this between any parameter you could think of. Irrespective, the normal distribution is still important, although for regression, it's not necessarily, yeah, that's a different concept. But essentially what you can do, you can compare two parameters that are seemingly unrelated to each other and seemingly have entirely different magnitudes and they gotta have the same distribution, but you can standardize them to SAT scores and they will get a SAT score that is comparable and allows them to make them comparable. And you can compare them directly. So that's the beauty of it. So, any questions to standardization, SAT scores? So here's another example And I'm trying to make this a little larger. Here's another example of standardization where this is important. So we're trying now to standardize here all emotions, and I don't know how they quantified this. I'm not a psychologist. Seems very difficult for me to kind of find a metric that quantifies all emotions, but seems to be possible. So we have now all emotions in black. We have fear in red, and we've discussed in blue. So obviously, three entirely different emotions. Well, different variables, and to make these comparable, you kind of have to standardize them. And there's dynamics that is here around the 1920s here. Yeah, well, obviously the world wars here, and the world war, things drop, they go back up. Well, here's actually a little bump. That bump could have been the Depression or something. Then I don't know, somewhere here we probably have the nuclear missile crisis, the whole Cold War story, and now it's just increasing again. So we have been pretty low, now we're going back up. But this gust is going down, so that's a good sign. So I don't know what this research entails, but essentially it is a way to get different parameters on one level. So it tells you where value fits into normal distribution. So yeah, it also can give you, and this is now interesting. And you remember that we have, so who of you remembers what an integral is? Did you integrate functions? Yeah, calculate the area under the curve. Yes, I see some nodding. There's only one nodding, Amira. So, but yes, exactly. That integral. It haunts you again because this is essentially the basis of the calculation of the area under the curve. And this area under the curve, and now think about it. You are using now a mean. The mean is exactly in the center of your normal distribution, right? The mean is in the center of your normal distribution. You're standardizing your normal distribution of set scores with a mean that you have calculated for your population. In the very same population, you have quantified your standard deviation. The standard deviation arithmetically incorporates your mean and each individual entry and the number of observations in your population. So this symmetric kind of bell-shaped curve, essentially you're characterizing it using standard deviations. If you do that, you can also do the quantification of what is called a percentile. This percentile essentially is characterizing how many percent of your population will be below this value. So now, in real life, when you think of it, think about it. Think about it, think of percentile. So where you basically, you think of, okay, so again, the blood pressure. Now let's not do the blood pressure. Let's do body weight. So now you think about 140 pounds, 150 pounds, 160 pounds, 170 pounds, 180 pounds, 190 pounds, up to like 250 pounds. So if you want to catch now your population and you want to characterize your population, it's like how many individuals are going to be less than 140 pounds? There's not going to be that many, right? But if you increase now your threshold and you go up to like 170, yeah, it's going to be more individuals have a weight less than 170. So now you go up to 250, which is like pretty decent weight already. You catch like half of the universe basically under those 250 pounds, right? And the same story is happening here because you have an average weight in your population, which is, let's say it's 100, 150. I'm used to the metric system in kilograms still. So it's hard for me to find really something that is realistic. But let's say 170 pounds. 170 pounds is an average weight. 160 pounds is an average weight. So this is our set of 0. And now we're going to the left. We have a standard deviation, so 160 pounds, and a standard deviation of, let's say, 30 pounds. So this is 190 pounds now. With 160, we are finding, as per definition, it's unimodal, symmetric, and bell-shaped. Everything below the mean is 50%. You go to the right, you add 1 standard deviation. At a set score of 1, you are catching 50% plus an additional 34%. And this is a definition thing. This is an arithmetic consequence of that function. So this function, when you use this to calculate that area under the curve and you integrate this function at a set score of 1, you will get 84%. Okay? This is what's happening. 50% up under the mean, plus 34%, 84%. Then you add another 14%, you're up at 98. You add another 2%, you're at 100. This is hypothetical. You also, and this is where it's getting interesting now, you can also employ something that is called the empirical rule. The empirical rule is the rule by a mathematician from Russia. Forgot his name. I'll look it up. I will post it. This empirical rule allows for you to quantify 3 things. It allows for you to quantify the percentage of your population that is within 1 standard deviation below the mean and 1 standard deviation above the mean. This arithmetically is 34, and 34 is 68% of your population. So if you have a normal distribution and you're adding 1, and usually data is depicted exactly in that way. If you look up a scientific article, you will find the normally distributed parameter. This is a mean plus minus a standard deviation. That's how it's, per definition, it's always reported. So you can, as a rule of thumb, you can take your mean and you can multiply the standard deviation by 2, and you go two standard deviations below, 2 standard deviations up, and then you capture 34 and 14 is 48. 34 and 14 is 48. 48 multiplied by 2 is 96. It's not 96, it's 95.7. They rounded. So essentially, within 2 standard deviations below and 2 standard deviations above, you capture 95%, 95.7% of your population. 68 was in 1 standard deviation up and down, so it's actually 2 standard deviations. 2 standard deviations down, 2 standard deviations up, including 4 standard deviations distance now, you get 95.7. You go an additional standard deviation up, which essentially is 6 standard deviations already. So 3 standard deviations below the mean, 3 standard deviations up from the mean. You capture 99% of your population. Okay, that's the empirical rule. I'm flagging this for the midterms. Good. Sample means a normal addition. Any questions? It's quite intuitive, right? It's a continuation of what we have been discussing. I encourage you to please rewatch the recording, go through the whole exercise, play around a little bit with the Excel spreadsheet. That's why I'm posting that stuff. Really do it. It will, yes, absolutely. Amira, please.
I just want to clarify, you said he allows us to quantify 3 things, which like it's like each standard deviation above the mean is the 3 things?
No, yes, these are the three things, yes. So one below and one above, so it gets us a distance of -1 and +1, so it's 2 standard deviations. Then it's the second thing is 2 standard deviation, 95.7, and the third thing is the 99. Yes, maybe it was not very well put, but yeah, these are the three things. That's what I meant. It's the empirical rule. So, yeah. And now we're coming somewhere totally different. And now I'm trying to build a bridge now. So we have, what do we have? We have 35 more minutes, good. So, okay, so now we understand normal distribution, raw scores, raw entries, happiness scores in countries, all good. Now we're going somewhat different, which essentially is also important to keep in mind. Because it's not only that the normal distribution per se is the basis of inferential statistics, also another construct is important. Essentially, you are looking at things in a way that you're trying to look at it in a way that you have taken samples from your population. So you're not characterizing an entire population, but you're characterizing samples of your population. And let's put it that way. You have again the blood pressure. So we have 100,000 people. We're drawing 100 people out of this 100,000 people. We're measuring all their blood pressure. We get one mean. We're throwing them all back in the pool. We sample another 100 random individuals. We quantify one mean. And we're doing that again, and we're doing that 100 times. What do you think is going to happen with the data? If you take 100 multiplied by 100, that's 10,000 people, right? If you would take from your population of 100,000 people, 10,000 individuals, and you're plotting their individual blood pressures, you get a very wide distribution, right? There's a lot of outliers, there's a lot of noise, and there's a lot of variability in your data. This is what we're seeing, like this Rubenesque kind of bell, right? There's a more elegant way to do that, because essentially you are really interested in the mean, and you want to understand the mean. How does your sample mean locate in relationship to your population mean? You're not interested in the variability. The variability is means to an end. You're really just interested in like, how does my population and average compare to the population? Or now, how does my sample population and average compare to the population? And for that very reason, you're taking not 10,000 people from your population and measure all the individual blood pressure. No, you're taking 100 multiplied by 100 samples. You're taking 100 times 100 individuals out of your population, absolutely randomly. We talked about random sampling, how important it is. You sample these out, you get 100 samples, you get 100 means. The mean of the means that you will get from these 100 samples is gonna be easier for you to interpret than this mean of 10,000 individuals, because the variability is going to be less. Because the mean of the means is still the mean. You don't have to worry about anything. It's like, so it will be the same mean if you do 100 multiplied by 100 samples as compared to 10,000 samples and or 10,000 individuals, and do all their means at the same time. Arithmetically leads to the same end. What changes is the variability. And it changes in a certain way and fashion And this is now a little bit tricky, and stay with me on the definition of this. The standard deviation of the population, if you have the population, this is going to be a wide distribution. The mean of the distribution, of the sample distribution, and the mean of the means of all your samples will be the same as the mean of the population, but the standard deviation will be different, because the standard deviation of the population or of your 10,000 measured blood pressures will be much wider than the standard deviation of the distribution and the standard deviation of the distribution of these means. And now I'm introducing to you what we will be actually working with for the rest of the semester. This is this connection between standard deviation and standard error of the means is what is called the central limit theorem. The central limit theorem is a relationship between the standard error of the mean, which is the distribution of the sample means. 100 samples of 100 individuals each, drawn from a population of 100,000. You're drawing 100 samples out, you get 100 means. These means distribute in a certain way. They're narrower than the actual scores and the standard deviation of the scores. The relationship between both is depicted here. It's the standard error of the mean, characterized here as sigma m equals sigma, which is your standard deviation, divided by the square root of the sample size of your sample. Sample, not population, sample. So this essentially equates now conceptually the relationship between the standard deviation and the standard error of the mean. And this will be very, very important down the road. So essentially, this is what we're looking at. So again, the country happiness scores, we have the distribution of the scores, we have the distribution of the means. So it becomes narrower, and the amount it's narrower is caused by the division of the square root of the n. So you take the standard deviation of this Rubenesque bell shape here, and you're dividing that by square root of the n. Sorry. You're dividing that by the square root of the n. What am I doing? You're dividing that by the square root of the n, and you at the distribution of the means. Okay, that's this relationship. Any questions on that? That's very central. Please ask questions. If you're not 100% on board with it, speak now, please. Good. All right, we carry on. Scores versus means. Another beautiful thing is the distribution of the sample means is more likely to be normally distributed, particularly when we talked about this, right? It's like the higher the sample size, and this is particularly true for the samples, size of the sample means. So if you have larger samples and you are basically looking at the distribution of the sample means, you will more likely have a normal distribution if you have a sample of 25 from the same population. Well, I don't know whether you use 25. It's like, so the common thing with statisticians is it's always the 30. I think I alluded to this at one point. It's like, it's always 30. You ask a statistician, how much sample size do you need? Statistician will tell you like 30. That's like, that's like the standard sample size that you will also see on the Z-score table and the T-score table. So yeah, you will hear that 30 more often. Okay, but it's 25 people. So this is skewed And you remember, please remember, this is right skewed. The tail tells the tail, right? So this is right skewed or positively skewed. This one too. This is normally distributed because you have larger samples. So the distribution of the sample means gets you back to normal distribution. So yeah. So the central limit theorem also allows for you to do the same thing as we did in the population, right? So if you are calculating a certain mean and you want to compare a mean to a population mean, and you have a standard error, obviously you can do the same thing as you did with the raw scores. You can basically, you take the mean, every individual mean. So now basically your x-axis is still a raw score, but it's basically your x becomes a mean, and you're subtracting still the population mean, right? So you're dividing it by the sample mean, and this basically gets you to a set score. And so it's the same concept, just with here the two distributions, right? So you can characterize the orange Rubenesque bell-shaped curve with the standard deviation, because that's the population. Those are the individual scores. Or you can characterize the actual standard errors, the sample means by the standard errors instead. By that, you essentially get the same set scores, where you get a set score of the means. And this allows for you to do hypothesis testing. And that, in turn, allows for you to compare means against each others. So you can compare your sample mean to a population mean. You can compare your sample mean to another sample mean. You can compare your sample mean of today to your sample mean from yesterday. And this is the hypothesis testing we're going to be doing for the rest of the class. And this hypothesis testing has exactly that relationship between means, sample means, distribution of the sample means, and their distribution characterized with the standard error of the mean in mind. So if you see a difference between two means, or the sample mean to a population mean, what you are essentially quantifying in hypothesis testing is whether this difference you're seeing is actually a real difference, or it's just a random difference due to chance. And if this probability that it's due to a chance, due to a random occurrence that has no meaning and no significance, is smaller than 5%, and that's the so-called p-value, you will reject your null hypothesis. And the null hypothesis, as you remember from last time, is that there's no difference, remember? And this p-value of 5%, you will be seeing at a set statistic, at a set score of 1.96, which is right here. And this set score of 1.96 is, interestingly enough, associated with an increase of frequency, which Nolan and Heinz now trying to make the point here that this is essentially the identification of cheaters, because everybody wants to have this significant kind of p-value or set score. So the set score translates in a p-value, and that's actually showing that it was actually significantly different, and I was actually able to reject my null hypothesis. And they think that the fact that there's an increased occurrence of SAT scores that are just across this board of 1.96 is an identification, or is basically caused by cheaters trying to make their results by all means significant, which would point towards a type 1 error, as we discussed last time. So I'm not sure I fully agree with that these are cheaters, but their point stands, and maybe something to discuss down the road. But yeah, it may require a second look. But yeah, so this is the whole principle. So we basically, what we're doing is, like, we have individual scores. We're characterizing a population using the assumption of a normal distribution, which is symmetric, unimodal, and bell-shaped. We're characterizing populations using SAT scores. Once we want to essentially look at sample means, we are taking samples, and we're taking repeated samples, and we're assuming that we're looking at a comparison of a mean of the means of several samples of a certain sample size, characterized by the so-called standard error of the mean, which is in a relationship to the population standard deviation by a division by the square root of the sample size. And the distribution of the sample means will be narrower than the distribution seen of the individual scores. And this essentially is then this distribution and this variability that you will be using for hypothesis testing. And this will basically be used in the way that you're quantifying SAT scores in your sample, in your distribution of the sample means, under the assumption that there were several repeated samples drawn from this population that led to this mean of the means. And you would use the calculation of the standard error of the mean to characterize your distribution of the sample means, and use this for hypothesis testing to compare the mean of the means, your hypothetical mean of means, to your population mean. This is the SAT statistic that we will be looking at in the next classes. We will not start hypothesis testing before the midterms. So next time we do confidence intervals, and only start SAT statistics after the midterms. But this is a concept, this will come to the midterms. So everything which we're currently doing is still part of the midterms. Okay, any questions? I know this was quite a hefty lecture. There were actually quite a bit of things we talked about, right? Any questions so far? Hannah? I saw the microphone go away. You have a question?
No, I don't. Sorry, that was an accident.
Okay, that's fine. Okay, so we have talked about this. We've talked about this. I just want to quickly show you live. And this is now R, and then you have the code on the module. So this is the happiness score. So this is essentially the same data frame as you have in Excel. I hope you all can see that. Same thing, you can do the same calculations. So now I want to create two sub-data frames, which is here a sample with 60 scores, random sampled from your overall data frame. So I create two of these data frames, which contain 60 happiness records, happiness scores. I quantify the means, and you see the means are substantially different, right? We have 5.64 and 5.22. If we look at the distribution, this is the distribution of the individual scores. This is not a nice normal distribution. This is the distribution of the second data frame, not a nice normal distribution. What I'm doing now is I will repeat this code and I will draw 20 different samples, all out of 60. And I will build a data frame that contains 20 of these means. So I get 20 samples, and each sample I calculate a different mean. And not a different mean, but I calculate this respective sample mean. So keep this in mind how that looks like. So now let's do this. So I have now 20 means. And when I plot this 20 means, I get this, which looks terrible. Okay, not a good example. Okay, let's try 200. Okay, okay, let's do 200. Okay, same story, 200 means. Now I have 200 means. Now I show this, and this becomes a normal distribution. Okay, good. Okay, now I made my point. So it's not a good example because it's repeated sampling. It's just I wanted to make this point. Hypothetically, it should be a large population, and you should draw from a large population. I just want to make the point that when you sample something repeatedly and you only take the sample means, you get this beautiful normal distribution, right? And this is the point. And the larger the samples are going to be, the more beautiful this distribution becomes a normal distribution. Good. Okay. This is all I have for today. 3 minutes before time. I'm really proud of myself. Any questions? Please give me questions, then I can keep on rambling on for the last 3 minutes. Otherwise, you can go. Let me know.
I have questions, but not on what we learned today, but on the homework.
Okay. Okay, we can discuss this after we concluded the lecture. Is this okay? If no further questions on the material, then please feel free to log off. I will stop the recording. And now I'm happy